Hello, Calculus and Vectors class. This is 5.4 rational functions. We're going to take a total 180 and we're going to flip from polynomials over to rational functions for a bit. In the last few lessons, we learned all sorts of tricks to graph polynomial functions. As it turns out, most of them are still useful, but there are some features of rational functions that we need to learn some more tricks before we can start dealing with rational functions. So we're going to take a break from the actual graphing, and we're going to do some review from advanced functions, talk about the features of a rational function and how we find them. So of course, hopefully at this point, you're aware that a rational function is a fraction that is formed by two different polynomials, f of x over g of x, where g of x cannot be equal to 0. So to find a few of these features, the first thing you should know is that if you can find some value of g of x that gives you it equal to 0, then that is a restriction in your domain. Next thing you need to know, intercepts. They actually essentially work the exact same way as with polynomials. All you do is you set h of x equals 0 or y equals 0 to find the x-intercepts, and you set y equals 0 to solve for the y-intercepts. So exact same thing. Let's talk about vertical asymptotes. So if f of x is approaching positive or negative infinity as x approaches a from the right or x approaches a from the left, then it's a vertical asymptote. So it might look something like, let's say this is the positive infinity option. Might look something like this. Or it might look something like this. Or sometimes we might just mix and match, all depending. In this case, on both sides, f of a would be approaching positive infinity, or f of a approaches negative infinity. But like I said, sometimes, as with the example of f of x equals 1 over x, they don't necessarily have to go the exact same way. So we just need to be able to tell where the asymptote is, along what line, and we need to figure out the direction of it. And then we can use that to help us as well as we're graphing. Let's talk about horizontal asymptotes. So with horizontal asymptotes, if h of x approaches L as x approaches positive or negative infinity, then y equals L is a horizontal asymptote. So your asymptote is going to fall along that line, y equals L. So let's say this is where x is approaching negative or positive infinity. So we're going all the way to the right of the graph, all the way to infinity. It's approaching that line y equals L. Or it could work the opposite way, where we have them going left towards negative infinity for x. And we're still approaching that line y equals L. So L is going to be some number, let's say maybe in this case it's y equals 2, where they're both approaching. So hopefully that's nothing new. What might be a little bit new is trying to figure out which way the asymptotes go and how to find them. Probably not, but just to be safe, we're going to do it. So with the vertical asymptote, we said vertical asymptotes appear whenever the denominator is equal to 0. So all we're going to do is set the denominator equal to 0, and we're going to see what happens. So x minus 2 is equal to 0, or x equals 2. So that means x equals 2 is going to form some sort of horizontal vertical asymptote. And now we just need to find, we know that with functions like this, usually there's a horizontal asymptote as well. But let's try and find that out. So to do that, we're going to think back to Unit 4, and we talked about limits towards positive and negative infinity. So we're just going to examine what's going on with this function as x gets closer to positive infinity. So that's going to be to the right of the graph. And towards negative infinity, what happens as we go towards the left. So to start, we're going to look just to the right and just to the left of that asymptote line. If you don't know the vertical asymptote just yet, you could just start anywhere and just keep going towards positive infinity. You just have to realize that sometime you're going to pass over that asymptote, and the first few numbers might not be relevant. So let's just start with x equals 3. Let's fill in our table of values. That's going to be 6. 3 plus 3 is 6. 3 minus 2 is 1 equals 6. And then we have, let's say, we're just going to pick larger and larger values of x. So we approach positive infinity. So if we did 100, it would be 103 over 98, or 1.05. Let's just pick bigger and bigger values. Let's see, let's go to 1,000,000. It's going to be 1.000005. So as you notice, with our values for y, the 1 stays in the same place, but the 5 keeps getting pushed smaller and smaller and smaller. So eventually, we're just going to be left with 1. So in this case, the limit as x approaches our infinity for our function is going to approach 1. So in this case, y is equal to 1 is going to be an asymptote line. But just to make sure, let's examine from the left as well. So just the left is 1. Let's do positive 1. And that's going to be 1 plus 3 is 4 over negative 1 is negative 4. Then we could do negative 1. That would be 3 minus 1 is 2 over 1 minus negative 2 is, that's going to be negative 0.667. And then we're just going to pick progressively larger values, getting closer to infinity, negative 0.95. Let's keep going. Negative 10,000 would be negative 0.9995. And you're noticing how I keep adding on 9s. In fact, if you did negative 1,000,000, it would be negative 0.999995. But you should notice that we approach, oh wait, those should be positives because we're dividing a negative by a negative, and they approach 1. So in this case, we get an asymptote around y equals 1 as well. The only difference is that now we're approaching from underneath the graph instead of over top. So take a look at the values. As we look from the right, we start at 1.05, which is just above, and then we get closer and closer. So we start above, and then, so it means that we're going to be going in this direction because all of our values for our right-handed limits, this one here, they all fall above that above that y equals 1 line. And you notice how down here we have 0.95, 0.9995. So they're all just a little bit below. So it means that when we plot them, they're going to all fall this way. And we know that asymptotes are kind of a dividing line. Generally speaking, we don't really cross over too much. Sometimes it happens, but in this case, with a simple one like this, it's never going to cross over the asymptote line. So it means that in this case, on the left of our vertical asymptote, we're going to be below, and to the right, we're going to be above our horizontal asymptote. You can confirm that by testing values really close to the vertical asymptote if you want to see what happens for that limit, just like we did in the last unit. But for right now, that should be sufficient. So now that we've done that, let's talk about one more type of asymptote that you've seen. Hopefully you've seen it before in advanced functions, but if not, we're going to cover it now. These are called oblique asymptotes. Now, oblique asymptotes are asymptotes. Sometimes they're called slant asymptotes. And essentially what they are asymptotes that occur on a diagonal. So in addition to having vertical and horizontal, we can have diagonal. Now, the big thing I want to stress to you guys is that we can always have vertical asymptotes. We can have horizontal asymptotes. We can have oblique asymptotes, but we're never going to have oblique and horizontal at the same time. So never oblique and horizontal in the same graph. And the reason for that is because hopefully in advanced functions you guys talked about the right-handed rule, and it says that if you take a ruler and you scan it left to right, you should never have more than 2 points on your graph. And if you have of a horizontal asymptote and a slant asymptote, then they're going to break that right-handed rule. So it means that those cannot exist in the same graph, in the same function. So the other thing that you need to know about oblique asymptotes is that they occur when the degree of f of x is 1 degree more than g of x. And the reason why that happens is because if we have 1 degree higher, let's say if we had a quadratic over a linear, it would actually work out so that way the quadratic is a degree 2 and the linear is a degree 1. So when you divide them out, in the middle, it doesn't look quite this way, but when you go towards infinity, all the stuff that happening in the middle becomes inconsequential. It starts behaving more like a linear function because when we divide out the degree 2 by the degree 1, it essentially turns into a degree 1, even though it doesn't look like it in the middle. Same thing if we had a cubic over a quadratic, then it would behave like a linear because the degree 3 and the degree 2 cancel each other out essentially. And again, like I said, it's not going to be that neat in the middle, but towards infinity, all that little stuff doesn't really matter. So essentially, the big thing to take away from that is you will have a slight asymptote when your degree in your numerator is exactly 1 more than your denominator. No more, no less. If you have a higher degree than that, then you're going to get something else completely. In fact, there are other types of asymptotes that can occur, but we're not going to deal with them right in this course. So now let's deal with trying to find the asymptotes for this function, x squared plus 1 over x minus 2. So first thing you should notice is that we have a quadratic over linear. So we're going to deal with an oblique, but let's start with the vertical because it's nice and simple. So vertical, we just said the denominator is equal to 0. So x minus 2 equals 0, or x equals 2. So that's going to be our vertical asymptote. And now to get your slant asymptote, now what we're going to do, we're going to try and take x squared plus 1 and divide it by x minus 2. Hopefully you've seen this method before using long division. If not, I will try and put some sort of video up to help you. There are plenty of them on YouTube, so if you can't find one in my stuff, then take a look on there. So essentially what we're going to do is we're going to try and divide this out. And so we're going to say, we're going to try and get rid of the x squared first. So we're going to try to figure out what we have to multiply x minus 2 by to turn it into an x squared. And we're going to have to take that and multiply it by an x. So now we multiply x minus 2 by x, and we get, that's going to be x times x is x squared, and then minus 2x. And then we're just going to subtract those two from each other. And we get, that's going to cancel out 0x squared. And then 0x minus 2x is going to be plus 2x. Then we carry down the 1. And we repeat. So now this time we have to get rid of the positive 2x. So we have to figure what we have to multiply our x minus 2 by to get a 2x in there. And the answer is we have to multiply it by 2. So 2 times x is going to be 2x. 2 times negative 2 is going to be negative 4. That's going to be negative 5. Oh wait, that's going to be positive 5 because we're subtracting. So from this, we get that this is going to be x plus 2. Then we have that remainder 5. But in this case, the remainder isn't the important part. X plus 2 equals y, or is the important part. So essentially, all we did here was we said y equals x squared plus 1 over x minus 2, and we just said if we're looking towards infinity, we just want to figure out overall what does this look like. All the middle stuff isn't too important to us. We're just looking towards infinity, and towards infinity, what this starts looking like is y equals x plus 2. That's going to be our oblique asymptote. So in this case, the function will approach the line y equals x plus 2 as x approaches positive or negative infinity. And because we have an oblique asymptote, we said we can't have a horizontal asymptote, so there's no need to solve for that. So now that we have that, we solve for the vertical asymptote, we solve for the horizontal asymptote, for the oblique asymptote. So we have all the asymptotes that we can find for this function. So just remember, use this long division method or synthetic division if you know that method. I'll try and post some links to help you out. But use that method if you're trying to solve for oblique asymptotes, which will occur if your numerator is 1 degree higher than your denominator. So that's pretty much it for this lesson. Check out the day 2 lesson, which will come in a separate video, and I'll finish off that before we head off into curve sketching with rational functions in 5.5. Thank you.